Welcome back to another lesson in MCV4U. Today we'll be looking at the intersection between two planes. So here when we look at the intersection of two planes, there's a few different possibilities that can occur. So the first possibility is that there's the intersection along a line. And here again, if there's an intersection along the line, there's infinite number of solutions along the line. And so what that means here is that the planes will have a line in common. The second possibility here is that there's two coincident planes. Two coincident planes. And what that means is, again, there's an infinite number of solutions along the plane. And so here that means that the planes will have collinear normals. So planes will have collinear normals and proportional d-values. Okay, and then lastly, again, there are going to be two parallel planes, non-coincident, again, and then therefore they would have no solutions. So here, to find the points of intersection between two planes, we're going to solve the system of equations formed by their Cartesian equations. So here we have plane number one would be represented by a1x plus b1y plus c1z plus d1 is equal to 0. And plane number two would be represented by the equation a2x plus b2y plus c2z plus d2 is equal to 0. So a couple of notes here. A normal to the first plane is a1, b1, and c1, and the normal to the second plane would be a2, b2, and c2. If the planes are parallel, then their normals will have the relationship n1 is equal to k n2 for some scalar value of k, which is an element of real numbers. And so here, again, here that means that the coefficients of a, b, and c are proportional. If the planes are coincident, then one equation is a scalar multiple of another. So here, again, the coefficients of a, b, c, and d are proportional. So if we look at example one, it says classify each pair of planes as distinct, so no POI, coincident, infinite POI along a plane, or intersecting, which is infinite POI along a line. Here it says, do not attempt to solve algebraically the system of equations. So here we have plane number one represented as the equation of 2x minus 3y plus z minus 1 is equal to 0. And plane number two is equal to 4x minus 6y plus 2z minus 2 is equal to 0. So here what we'll do is we'll take our equation of our first plane and we're going to multiply that by 2. And what that's going to give us is it's going to give us 4x minus 6y plus 2z minus 2 is equal to 0. And what we notice here is that the equation for plane 2 would be the same, 4x minus 6y plus 2z minus 2 is equal to 0. So therefore, what we see here is that, again, it has the same plane, and therefore they are coincident And here therefore, there would be an infinite number of COI. Another way that we can solve this is we can look at the normals. So again, here are the normals. So for plane number 1 would be 2, -3, and 1. And the normal for plane number 2 would be equal to 4, -6, and 2. If we take that and divide that by 2, that'll be equal to 2, -3, and 1. So here we see that they have the same normal. And if we look at the d value, so if we look at the d value for plane number 1, that's equal to -1. And here, if we look at the d value for plane number 2, that's equal to -2. If we divide that by 2, we'll get also -1. So again, the normal values are the same, and the d value is also the same. Here, if we look at E, so plane number 1 is represented by the equation 3x plus 6y minus 9z minus 3 is equal to 0. And plane number 2 is represented by the equation 2x plus 4y minus 6z minus 4 is equal to 0. And what we'll do is we'll take our first equation for our plane, and we're going to multiply that by 2, multiply that by 2, and that's going to give us 6x plus 12y minus 18z minus 6 is equal to 0. Here, if we take our second plane equation, we'll multiply that by 3, we'll get 6x plus 12y minus 18z minus 12 is equal to 0. Here, what we see is that our normals are going to be the same. So here, the normal for our first plane is equal to 6, 12, and -18. And our normal for our second plane is 6, 12, and -18. So those are the same here. But here we see that our d value for plane number 1 is -6, but our d value for our plane number 2 is -12. So those would not be equal to each other. So what that means is that, again, these planes would be parallel, and therefore there would be no points of intersection. And so for C here, we have plane number 1, the equation is represented by x plus 2y plus 3z plus 1 is equal to 0. And plane number 2 is represented by the equation 3x plus 2y plus z plus 1 is equal to 0. So here we'll take our first equation, and we'll multiply that by 3. That'll give us 3x plus 6y plus 9z plus 3 is equal to 0. And for our second plane equation, that's equal there to 3x plus 2y plus z plus 2 is equal to 0. And so here we see that the normal for the first equation does not equal the normal for the second equation. And so here what that means is that, again, the planes will intersect along a line, Planes intersect along a line. Therefore, infinite solutions along a line. Okay, example number 2 says to find the point or points of intersection of the following two planes, give a geometric representation of the solution or solutions. So here, what we want to do is we want to check if the normals are parallel. So we want to check if the normals are parallel. And so here, if we take first plane equation and we multiply that by -4, that will give us -4x plus 4y plus 8z minus 4 is equal to 0. And our second plane equation will be -4x plus 4y plus 8z minus 3 is equal to 0. So here we see that our normals will be the same. So normal 1 is equal to normal 2. However, our d values are not the same. So d1 does not equal to d2. Here we see that if we look at this, the planes will be parallel to each other. So therefore, again, planes are parallel and distinct, and there'd be no points of intersection. Okay, so example number 3 says find the points of intersection of the following two planes. Give a geometric representation of the solution or solutions. So plane number 1 is x minus 2y plus 3z plus 1, and plane number 2 is -3x plus 6y minus 9z minus 3 is equal to 0. So here, if we look at our first equation for plane number 1, we'll multiply that by -3 to give us the equation -3x plus 6y minus 9z minus 3 is equal to 0. And here for plane number 2, again, we have -3x plus 6y minus 9z minus 3 is equal to 0. So here, again, we see that they are the same, and therefore these are coincident, and therefore we have infinite points of intersection. Okay, so here, in terms of our points of intersection, what we want to do is we want to show it in parametric form. Okay, so here we write plane number 1 is x minus 2y plus 3z plus 1 is equal to 0. And here what we're going to do is we're going to isolate for x. If we isolate for x, we get x is equal to 2y minus 3z minus 1. And here what we want to do is we want to pick some parameters for y and z. Here, pick parameters for y and z. And so for example here, what we'll do is we'll let y is equal to t, and z is equal to s. And so here, point of intersections along the plane written in this parametric equation would be x is equal to 2t minus 3s minus 1, y is equal to t, and z is equal to s, here where s and t are an element of real numbers. Okay, so finally here, example number 4 says find the point or point of intersection of the following planes. The following two planes we have here. The first equation is equal to negative 2x plus 3y plus z plus 6 is equal to 0. And our second equation is 3x minus y plus 2z minus 2 is equal to 0. So here for our first equation, we're going to multiply that by negative 3, and that will give us 6x minus 9y minus 3z minus 18 is equal to 0. Our second equation, we're going to multiply that by 2, and that will give us 6x minus 2y plus 4z minus 4 is equal to 0. Here we see that they are not parallel because their normals are not the same. So not parallel. And therefore, we need to solve for points of intersection along the line. So if we look at our first equation here, we have negative 2x plus 3y plus z plus 6 is equal to 0. And again, here we're just going to isolate for z again, since it already has a coefficient of 1, and so it just makes it easier. So here we get z is equal to 2x minus 3y minus 6. So z is equal to 2x minus 3y minus 6. Take that, and we're going to sub that into the plane 2 equation. And so here, our plane 2 equation will be 3x minus y plus 2 times 2x minus 3y minus 6 minus 2 is equal to 0. So we sub 2x minus 3y minus 6 in for z. If we expand that, we get 3x minus y plus 4x minus 6y minus 12 minus 2 is equal to 0. That'll leave us with 7x minus 7y minus 14 is equal to 0. So here, if we isolate for x here, we will get x is equal to 2 plus y. Here we have x is equal to 2 plus y. We have z is equal to 2x minus 3y minus 6. And so here, since we found expressions for So here again, since we found expressions for x and z, again, now we will again use parametric equations to create the line. Okay, and then we'll also create our parameters here. For our parameters, we're going to here let y is equal to t, and if we do that, then x is equal to 2 plus t. Okay, so here x is equal to 2 plus t, and if we sub that in as well, we have again z would be equal to 2 times 2 plus t, which was x, minus 3t, the t was y, minus 6, which is equal to 4 plus 2t minus 3t minus 6, and so z would be equal to negative 2 minus t. And so that gives us our x, y, and z equations. So here, therefore, x is equal to 2 plus t, y is equal to t, and z is equal to negative 2 minus t. So here, t is an element of real numbers. Here it says find the direction vector of the line of intersection. Okay, so therefore on each, that means on each plane of the two planes. Okay, so here what we see is the normal one to plane one is orthogonal, is orthogonal to line of intersection. And we also see that the normal, the normal of the second plane to plane number two is also orthogonal to the line of intersection. Okay, so here to find, that means to find again here our direction vector of the line of intersection, we will find the cross product. So we'll find the cross product between the normal one and normal two. So that's equal to the direction vector of line of intersection. Okay, so here we get the first normal is equal to negative 2, 3, and 1. And the second normal here is equal to 3, negative 1, and 2. And so here, when we look at our cross product between the two, we have negative 2 and 3. We have 3 and -1, 1 and 2, and then we rewrite the first two again. So here we have -2 and 3, and we have 3 and -1. Remember, we ignored the first line here, then we cross the rest. So here, again, what that gives us with the cross product is we get 6 minus -1, 3 minus -4, and 2 minus 9. So that's equal to 7, 7, and -7. Divide all of those by 7, we'll be left with 1, 1, and -1 as our direction vector. So here, if we draw our planes, we have our first plane, something like this. Our second plane will look something like this here. And we have our normal for our first plane. And here that creates our 90-degree angle. So normal for our first plane, our normal for our second plane, and then again, here, our direction vector is going to be right down that middle that would intersect the two planes.